This is Physics 2120, Lecture 4, and today we're going to continue talking about Gauss's law. Remember, Gauss's law says that the electric flux is equal to the integral of E dot dA in a closed surface, and it's equal to the charge enclosed over epsilon naught, where Qn is the net charge inside the surface, E represented the electric field at any point on the surface. And although Gauss's law can in theory be solved to find E for any charge configuration, in practice we really limit it to symmetric situations. To use Gauss's law, you want to choose a Gaussian surface over which the surface integral can be simplified and the electric field is determined. We're going to take advantage of symmetry, and remember, the Gaussian surface is a surface you choose. It doesn't have to coincide with a real surface. So to use Gauss's law, you want to choose a Gaussian surface over which the surface integral can be simplified and the electric field determined. We're going to take advantage of symmetry. And remember, the Gaussian surface is a surface you choose. It does not have to have a real surface. So we're going to try to choose a surface that satisfies one or more of the following conditions. This value of the electric field can be argued from symmetry to be constant over the surface. The dot product of E dot dA can be expressed as a simple algebraic product EdA because E and dA are parallel, or the dot product is 0 because E and dA are perpendicular. Or you can argue that the field is 0 over the surface. So let's apply this to a simple situation of a point charge. So I know that from a point charge the electric field comes off radially. So let's choose a Gaussian surface that is a sphere with the point charge at the center of the sphere. And if we do that, we see that the electric field and dA are parallel to each other at every point on the surface. So if that's true everywhere in this integral, E dot dA just becomes EdA. And E also, from symmetry, has to be constant. We know that electric field has got to be the same at a distance away from this charge, because no matter which way I rotate the charge, it can't change the electric field. So if that's the case, if the electric field is constant along my surface, it comes out of the integral. And so I just end up with the integral of dA. Well, that would just be the area of the surface, which the surface area of a sphere is 4 pi r squared. So E times 4 pi r squared, we see, is just equal to Q over epsilon naught. So now let's solve for E. If we solve for E, we just divide by 4 pi r squared. We see that electric field is Q over 4 pi epsilon naught r squared, and 1 over 4 pi epsilon naught is K sub E. So electric field is KQ over r squared. That's exactly what we said it was. We didn't use the fact that it was KQ over r squared. All we did is we argued due to symmetry that the electric field has to be the same no matter what direction you are from that point charge. And Gauss's law then shows that the electric field of a point charge is KQ over r squared. Well, what about a different thing? What if we have a spherically symmetric charge distribution? So let's assume I've got a sphere of charge, radius A, and that charge is uniformly distributed everywhere. What shape should we use for the Gaussian surface? I want you to think through this for a second. What shape could we use that the electric field could be argued to be constant over the surface, or that the electric field, due to symmetry, has to be perpendicular or parallel to the surface? All right, do you have your surface in mind? Let's see. We're going to choose a sphere for the Gaussian surface. All right, so we know the flux is the integral of E dot dA. Now, this charge is spherically symmetric, so no matter which way I rotate it, the electric field can't change. That means the electric field has to only depend on the distance away from the center. So at a certain distance away, distance r away, E has to point radially outward, and it has to be constant. So E dot dA becomes E dA. E comes out of the integral again, and we're just integrating dA, so it's E times 4 pi r squared. Anytime I have a spherical Gaussian surface, the integral of E dot dA is going to be E times 4 pi r squared. And that's just equal to the charge enclosed over epsilon naught. So, the charge enclosed is just Q, so the electric field is Q over 4 pi epsilon naught r squared, or KQ over r squared. Exactly the same as a point charge when I'm outside the spherically symmetric charge distribution. What about if I want to know the electric field inside the sphere? Well, I still have the same symmetry, so we're still going to choose a sphere as our Gaussian surface. But now we're going to draw our Gaussian surface inside the sphere. Right? So r is the distance away from the center that we want to know what the electric field is, and a is still the size of this charged sphere. So we know that the charge density for this spherically symmetric, we know rho is equal to Q over the volume, which will be Q over 4/3 pi a cubed. That's the volume of the sphere. The volume enclosed by my Gaussian surface is 4/3 pi r cubed. So the charge in this region here is the density times its volume. So rho times the volume enclosed. So that's going to be Q over 4/3 pi a cubed times 4/3 pi r cubed. Or the charge enclosed is Q times r cubed over a cubed. So I can use this fact here now and say, well, the integral of E dot dA, everything is the same for this for the sphere. It's integral of E dot dA becomes E dA. It's just E times 4 pi r squared. It's charge enclosed over epsilon naught. Or E is charge enclosed over 4 pi epsilon naught r squared, which is K times Q over a cubed r. So inside the sphere, E varies linearly with r, and E goes to 0 as r goes to 0. The field outside the sphere is equivalent to that of a point charge located at the center of the sphere. So if I were to map or graph the electric field, it goes linearly upward, and then it comes down like 1 over r squared, like it was a point charge. So next, let's consider a thin spherical shell. Like a basketball is hollow on the inside and has a thin shell. And this thin shell has a charge Q on it and a radius A. So what shape should we use for the Gaussian surface? I'll give you a few seconds to think about it again. Okay, have you thought about it? Let's go on. We're going to use, again, spheres, because if it's a spherical shell, it still has spherical symmetry. So, when r is bigger than A, all the charge Q is on the inside, and so we know then that the electric field is equal to KQ over r squared. We could work out the integral, but it's exactly the same as the last example we looked at. When r is less than A, when my Gaussian sphere is on the inside of it, there is no charge inside the surface, and therefore the electric field is 0. So now we know it's 0 inside, KQ over r squared on the outside, and we know what the electric field is everywhere. All right, let's say I have a long line of charge. What shape should we use for the Gaussian surface here? In this case, we're going to use a cylinder. So the cylinder has a radius r and a length L. Now let's think about this. If this is a very long wire the electric field has to point radially outward from the wire, because if I were to look at some point here, the electric field at this point might point in this direction, but there's another one here that cancels out, and so all the electric field has to point radially outward. So E is constant magnitude and perpendicular to this cylinder on every part of the curved surface. On the top and bottom of the cylinder, the electric field is perpendicular to dA. dA would point up on the top. Therefore, there's no flux through the top or the bottom. You can confirm this by looking at this from a top view. The electric field from this charge is going to point radially outward in all directions. So the field through the end of the cylinder is 0 since it's parallel to those surfaces. So then we use Gauss's law to find the field. Right? The integral of E dot dA, in this case, we know that the integral over the top and bottom surfaces is 0, and on the sides E is constant, so EdA becomes just EdA. Electric field comes out, so electric field is 2 pi RL. That is the surface area of a cylinder. 2 pi r is the circumference of the circle times the height, L. And that's equal to the charge inside. Well, the charge inside, it's got a linear charge density lambda times the length of the cylinder. That's all that is in that cylinder divided by epsilon naught. Notice that the L's cancel out so that I don't have to worry about how big my cylinder is. It doesn't matter how big my cylinder is, it all goes away. And then the electric field is lambda over 2 pi epsilon naught r, or 2k times lambda over r. So the electric field goes like 1 over r from a long wire. All right, what if I had a charged surface, a plane of charge? What shape should we use for our Gaussian surface? Now this is a little more tricky, so just think about it for a second. Let's say I've got a large plane, it's got a total charge q. What shape would I use? In this case, we'll use what Gauss called a Gaussian pillbox. It could be a square box or a round cylinder like shown in the picture. It really doesn't matter. Because if it's a plane, then we know that the electric field has to point straight away, perpendicularly away from the plane. So the sides of the box don't matter. The sides of the box have no electric field through it. The only electric field is going through the surface and the back surface. And we draw our Gaussian surface so that it is bisected by this plane of charge. So E is parallel to the curved surface, and there's no contribution to the surface area from the curved part of the cylinder. The flux through each end of the cylinder is E times A. So then the total flux through the cylinder is just 2 times E times A. The total charge inside the surface is the surface charge density, sigma, times the area. So if we apply that to Gauss's law, integral V dot dA we said was just 2EA, and that's the charge, sigma A over epsilon naught. And again, like before, it doesn't matter how big my Gaussian box is because the areas are going to go away. And then the electric field is just sigma over 2 epsilon naught. Now this is a theoretical problem. It's got a theoretical answer because notice that it's uniform everywhere. It doesn't depend on how far away you are. We've assumed that I have an infinite sheet charge, so if I have something that's infinitely large, the electric field is constant everywhere. I can't really ever create an infinite charge, but I can create something that might look like infinity. If, say, the table in front of you was all charged, and I want to know what the electric field was maybe a millimeter above the table would look infinitely big compared to the distance above the table. Now, understanding Gauss's law is very important. You will see a Gauss's law problem on an exam. I will guarantee it. Now, next thing I want to talk about is electrostatic equilibrium. When there's no net motion of charge in a conductor, the conductor is said to be in electrostatic equilibrium. Now there's some properties of a conductor you need to know that are in electrostatic equilibrium. Number one, the electric field is zero everywhere inside the conductor. 2. If an isolated conductor carries a charge, the charge resides on its surface. 3. The electric field just outside a charged conductor is perpendicular to the surface and has a magnitude sigma over epsilon naught, where sigma again is the surface charge density. And 4. On an irregularly shaped conductor, the surface charge density is greatest at locations where the radius of curvature is smallest. Now let's look at these. Property 1 says the electric field inside a conductor is zero. Let's consider a conducting slab in an external field E. If the field inside the conductor were not zero, electrons in the conductor would experience an electrical force and they would accelerate. Those electrons would not be in equilibrium. Therefore, there cannot be a field inside the conductor. So before the electric external field is applied, free electrons are distributed throughout the conductor. When the electric field is applied, the electrons redistribute themselves until the magnitude of the internal field equals the magnitude of the external field, but in opposite direction. Therefore, there's a net field of zero inside the conductor. And that redistribution takes place almost instantaneously. It takes about 10 to the minus 15 seconds. All right, property 2, we said charge always resides on the surface. So here we have our physics potato here. It's a charged, it's just a conductor. Let's say I've got a Gaussian surface, and we're going to draw our Gaussian surface inside, but as close as possible as we can to the actual surface. Now, in equilibrium, we know that the electric field in here is zero. And if the electric field is zero everywhere inside the conductor, that means there can be no flux going through the conductor. If there is no net flux through that Gaussian surface, and because that Gaussian surface can be as close to the actual surface as desired, there can be no charge inside the surface. Since no net charge can be inside the surface, any net charge has to reside on the surface. Gauss's law doesn't tell us how these charges are distributed on the surface, only that any charge has to be on the surface of the conductor. Property 3 talks about its magnitude and direction. We choose a cylinder as our Gaussian surface. The field must be perpendicular to the surface. If there was a component of the electric field that was parallel to the surface, then any charges here would experience a force and would move along the surface. So, if that was the case, it wouldn't be in equilibrium. So if it's in equilibrium, there can be no electric field parallel to the surface. It always has to be perpendicular. And the net flux through the Gaussian surface is only on the flat face outside the conductor. And the field here is perpendicular to the surface, so I draw my Gaussian pillbox as small as possible, and in this case it's EA is equal to the charge on the surface, which was sigma A over epsilon naught, or the electric field is sigma over epsilon naught. Now, if I have some conductors, and here I have some conductors, and I have some iron filings, they're going to line up with my electric field lines. We see the field lines are perpendicular to both conductors, no matter if I'm looking at the top, along the side, or around the curved surface. The electric field is perpendicular everywhere. I also know that, notice that inside, if this black is a conductor that's got charge on it, inside we see there's no electric fields because all charge has to reside right along the outside of the conductor. So, to review what we talked about today, we talked about Gauss's law and how to apply it when symmetry is present to easily solve for the electric field. And just recently, at the end, we talked about the four properties of conductors.